This is the first of two videos looking at the work on momentum, impulse and collisions for Unit 6 of the WJEC Further Mathematics specification. Specification simply says that we must be able to understand the concepts of momentum and impulse in two dimensions, making use, where necessary, of vectors. So there's quite a large amount of overlap between this unit and the work that you have already done in FM3. So, the momentum of a body is given by m times v, where v is the velocity of the body, which of course means that momentum is a vector quantity. The impulse of a force F acting for time t seconds is F times t, which again means that impulse is a vector quantity. And we have the important relationship that the impulse acting on a body is equal to the change in momentum of the body. In other words, the final momentum of the body minus the initial momentum of the body. And that is an immediate consequence of Newton's laws of motion. And the conservation of momentum states that if there are no external impulses acting, then the total momentum of a system immediately before the interaction will equal the total momentum of the system immediately after the interaction. So for our first example, we have Luca kicking a football to Austin, and just before Austin kicks the ball, it is travelling horizontally at 2.6 meters per second. Immediately after Austin has kicked the ball, it is travelling horizontally at 4.4 meters per second in a direction that makes an angle of 35 degrees with the original direction of motion. And we have to find the magnitude and the direction of the impulse of Austin's kick. So we need to start with a diagram, and because we've got things happening in two dimensions, we need to be fairly clear about setting up some axes so we can express the velocities using vectors. So we're going to arrange the axes so that the direction of the initial velocity is the positive x direction. So our initial velocity is 2.6 meters per second in the positive x direction. After Austin has kicked the ball is moving horizontally at 4.4 meters per second, making an angle of 35 degrees with the original direction of motion. So the ball has received a kick, an impulse from Austin, and after it has received that impulse, it is moving off with a speed of 4.4 meters per second at an angle of 35 degrees to the original direction. Now we can now express the initial velocity and the final velocity as vectors. So the initial velocity is simply 2.6 in the x direction and nothing in the y direction. The final velocity is 4.4 cos 35 in the x direction and 4.4 sine 35 in the y direction. And we can now find the impulse as a vector using the fact that the impulse is the change in the momentum. So that is the final momentum minus the initial momentum. The final momentum is the mass of the ball, 0.42 kilograms, times by the final velocity, which was 3.604, 2.524. Whereas the initial momentum is the mass of the ball, 0.42, times by the initial velocity, which was 2.60. So that now gives me the impulse as a vector is 0.422 in the x direction and 1.060 in the y direction. So we can draw a quick little diagram to picture this impulse. So we've got a x component of the impulse is 0.422, a y component is 1.06. So using Pythagoras, we can obtain the magnitude of the impulse. So the magnitude of the impulse is the square root of 0.422 squared plus 1.06 squared, which gives me 1.14 Newton seconds. And the direction of this impulse, well, the impulse is making an angle theta with the x direction, where tan theta is 1.06 divided by 0.422. So theta is the inverse tan of 1.06 divided by 0.422, which is 68.3 degrees. Now for our second example, we have a rocket of mass 10m is moving with velocity 20i plus 30j. So that's a vector velocity of 20 in the x direction and 30 in the y direction when it explodes and separates into two parts. Immediately after the explosion, the smaller fragment has a mass of 2m and a velocity of 5a plus 45j. Making clear that any assumptions that we've made determine the velocity immediately after the explosion of the larger fragment. Well, we're going to assume that the larger fragment has got a mass of 8m. In other words, there has been no mass loss during the course of the explosion. The momentum of the whole system will be conserved during the explosion because there are no external impulses acting during this explosion. So we can say that the initial momentum, which is 10m times by the vector 2030, must equal the final momentum of the system after the explosion. So that is 2m times the vector 545 plus 8m times the velocity of the larger portion, which is the vector v. So that means we can cancel the m's out throughout that equation and obtain the simpler equation. Vector 200, 300 must be equal to the vector 10, 90 plus 8 times the velocity of the larger fragment. And simplifying that, we obtain v equals 23.75, 26.25, which is the same as 23.75 I plus 26.25 J. Second part of the question, we need to calculate the increase in the kinetic energy of the system during the explosion. We know that the velocity of the larger part after the explosion is 23.75, 26.25. We know that the velocity of the smaller part after the explosion is 545. And we know that before the explosion, the velocity of the rocket was 2030. 30. So we'll start off by working out the kinetic energy of the system before the explosion. So before the explosion, the rocket was moving with velocity 2030, which means that its speed was the square root of 20 squared plus 30 squared, in other words, the square root of 1300. The kinetic energy before the explosion is therefore a half times the mass of the rocket, which is 10 m, times by u squared, which in other words gives us a half times 10 m times 1300, or 6500 m. The kinetic energy immediately after the explosion is going to be the kinetic energy of the small fragment plus the kinetic energy of the large fragment. The kinetic energy of the small fragment is going to be a half times 2m, that's the mass of the small fragment, times by the speed of the small fragment after the explosion squared. We know the velocity of the small fragment after the explosion was 545, so the speed of the small fragment after the explosion will be the square root of 5 squared plus 45 squared. So the kinetic energy of the small fragment after the explosion is going to be a half times 2m times by the square root of 5 squared plus 45 squared squared. Similarly, the kinetic energy of the large fragment immediately after the explosion is going to be a half times by 8m times by the square root of 23.75 squared plus 26.25 squared, which is the speed of the large fragment, squared. Which gives us 2050 m plus 5012.5 m, or 7062.5 m. So the increase in the kinetic energy is the difference between the 7062.5 m and 6500 m, which is namely 562.5 m. The final part of the question asks us to give a reason for giving a brief reason for our answer. Describe what can be said about the energy released during the explosion. Well, we've seen that we've got a kinetic energy increase, but the explosion is also likely to have involved a bang and quite likely some light. So that kinetic energy increase is going to only be part of the energy release of the explosion. So what we can say is that the energy released during the explosion is likely to be more than 562.5 times m. We now consider an example from the M3 paper from 2015. We have two particles, A and B, which are attached to each end of a light inextensible string of length √3 times L. Initially the particles are at rest on a smooth horizontal surface a distance L meters apart as shown in the diagram. Particle B is then projected horizontally with speed 8 meters per second at an angle of 60 degrees to the line joining the initial positions of A and B produced. We're told that immediately after the strings become taut, that we have to show that the particle A starts to move in a direction which makes an angle of 30 degrees with the initial line joining the positions of A and B. And we have to find the speed with which each particle begins to move and the magnitude of the impulsive tension in the string. Now on this example we've got to be very careful to build things up slowly and steadily and make sure that we understand what is happening. So we'll try and draw the diagram just before the string goes taut. Now just before the string goes taut, A will still be stationary in its initial position, but B will have moved for a length of time with a constant velocity of 8 meters per second at 60 degrees to the initial line joining A and B. So our picture is going to be like that. Now we know that the length of the line joining A to the original position of B is L, and we know that just before the string goes taut, the length of the line joining A to B is going to be root 3L. We also know that the angle from the original position of B to this new position of B makes an angle of 60 degrees with the line joining A to the initial position of B. So because we've got 60 degrees there, the remainder of that angle, the angle inside the triangle, the obtuse angle inside the triangle must be 120 degrees. And we could do with trying to find the angle theta, or equally well the angle alpha, and we can do this using a little bit of trigonometry, namely the sine rule. So we've got sine 120 divided by root 3L is the same thing as sine alpha over L. So sine alpha must be sine 120 divided by root 3, which is a half. So alpha must be 30 degrees because we know that alpha must be an acute angle. And that means that theta is also going to be 30 degrees using angles in a triangle. So there's the picture that we've got just before the strings go taut. Now, as the string goes taut, we are going to have an impulse acting on A and jerking A into motion. And we're going to have an equal and opposite impulse acting on B, which will certainly have an effect on the momentum of particle B. Now at this stage we haven't yet set up any vector system, so we need to think about axes, and it really makes a very good idea to have one of the two axes running along the length of the string at the instant when the string goes taut. So we're going to define our x-axis as being in the direction A to B at the instant when the string goes taut, and the y-axis is going to be perpendicular to that direction. So there we are, we've got our x-axis and our y-axis now defined. So we now need to try and write the initial velocity of B, which we know is acting at an angle of 60 degrees to the initial line joining A to the initial position of B, which means that it is acting at an angle of 30 degrees to the line which is defining our x-axis, which means that the initial velocity of B can be written as a vector of 8 cos 30 8 sine 30. So, just before the strings go taut, we've got our 8 cos 30, 8 sine 30 going on. Now we want to think about what happens after the strings go taut. So after the strings go taut, the velocity of A will be in the direction of AB because its initial velocity is 0. It's experiencing a jerk along the string. So it will start moving in the direction of the string, which is at 30 degrees to the line joining the initial positions of A and B. So in other words, A will be moving along the x-axis. So let's say that A now has got a velocity of v in the x direction, and we know the velocity of A is entirely in the x direction, so therefore it's going to have a 0 component in the y direction. Now the second thing, and this is really important that we have to take into account, is that since the string is now taut, the component of B's velocity along the string, in other words, the component of B's velocity in the x direction, must be the same as the velocity of A in the x direction. Because otherwise the string wouldn't be taut and the string wouldn't be inelastic or inextensible. So that means we know the x component of the velocity of B must be v. Now B is experiencing an impulse along the string. So that means that there is no impulse in the y direction, so the y component of its velocity is unchanged as the strings go taut. Now we know that initially, before the strings go taut, the y component of the velocity of B was 4. So that means after the strings go taut, the y component of the velocity of B must be 4. So we know that the velocity of B after the strings must go taut must be v in the x direction, since the strings are taut and inextensible. Sorry, the string is taut and inextensible. And since there was no impulse on B in the y direction. So we have the velocity of B after the strings go taut is v in the x direction and 4 in the y direction. Now that we've set those diagrams up, and I think you'll agree that setting those diagrams up has been quite a lengthy process, we can now start applying the mechanical principles, which are going to be impulse equals change in momentum. We first of all apply that to A. A has an impulse of j in the x direction and 0 in the y direction acting on it, equals the final momentum of A, which is the mass of A, 3, times the vector v0, take away the initial momentum of A, which is 3 times 0, 0. And applying the impulse equals change in momentum equation to B, the impulse acting on B is minus j in the x direction and 0 in the y direction. So we've got minus j, 0 is the impulse, equals the final momentum of b, which is 5 times the vector v4. Take away the initial momentum of b, which is 5 times 8 cos 30, 8 sine 30. So looking at the two x equations that we've got j equals 3v, and we've got minus j equals 5v minus 20 root 3. Adding the two equations gives me 8v minus 20 root 3 equals 0. In other words, v must be 20 root 3 divided by 8, which cancels down to 5 root 3 over 2. And the fact that we know that j is 3v means that we now know that j is 15 root 3 over 2. So, now that we've found v and j, we just need to make sure that we've answered all the different bits of b. So, the speed with which a begins to move after the strings have gone taut is just v, which is 5 root 3 over 2, or roughly 4.33 meters per second. The velocity of b just after the strings go taut is given by the vector v4. So the speed of b is the square root of v squared plus 4 squared, which gives us roughly 5.89 meters per second. And the impulse, or the magnitude of the impulse, is the size j, which is 15 root 3 over 2, or roughly 12.99 Newton seconds.